So in this video, we're going to go over an example where we test for concavity, where we are working with a rational function. So it says determine the intervals on which f of x equals 24 over x squared plus 12 is concave up or concave down. I've included a picture of f of x right here just to help us think about the problem and what the solutions ought to be. So not only have I included f of x, but I've included the second derivative of f, so f double prime of x. And f double prime tells us all the things that we need to know about the concavity of our original function f of x. So if we just look through the graph to figure out the solutions first, we can then walk through the calculus of figuring out our intervals of concavity. So first thing is we need to establish inflection points on our graph. And inflection points are going to happen when either the second derivative is equal to 0 or undefined. So I see that my second derivative is 0 here and here. So that's going to correspond to the inflection points on the graph of f of x here and here. The second derivative is positive or above the x-axis here. So I know from negative infinity up to this first inflection point when x is negative 2, because the second derivative is positive, I expect my graph of f of x to be concave up. But between negative 2 and 2, these two inflection point values for x, I see that the second derivative is negative, so I expect my graph to be concave down between those two values of x. And here the second derivative is positive, so once I get past 2, I expect my graph to be concave up. So that's what I expect based on a graphical analysis. So let's walk through using calculus to come to those same conclusions. So step 1, when we're testing for concavity, we want to look at the function and identify the domain of the function. So the first thing I want to realize is that I do have a rational function. So I have a 0-degree polynomial in the numerator and a second-degree polynomial in the denominator. So the bad things will happen if I get a division by 0. So I have to ask the question, can x squared plus 12 ever equal 0? And the answer is it can't for the real numbers. So over the real number line, if we tried to set x squared plus 12 equal to 0, we're going to get x squared equals negative 12. So we would get x equals plus or minus the square root of negative 12. And because it's the square root of a negative, this is a complex number. So I see that I don't have any real number zeros, which means that my graph of f of x has domain from negative infinity to infinity. So that's the first thing to think about and check for. What is the domain of my function? Because we use the domain in conjunction with the x values for the inflection points to establish our test intervals. So once we have done that, we want to find our inflection points, or the x values for the inflection points. So I'm going to take my function f of x, and I want to recognize that this can be rewritten as 24 times, I can bring the x squared plus 12 up into the numerator position as long as I take that first power exponent and make it a negative 1. So I need to know the second derivative to find the inflection point. So I first need to calculate the first derivative, which is going to be 24 times the negative 1 in the exponent position will come down. I get x squared plus 12. I have to subtract 1 from that exponent using the power rule, so I get negative 2 times. The chain rule says multiply by the derivative of the inside function, which is twice x. And then we want to look at this and simplify things a little bit. So I have 24 times negative 1 times 2. I get a negative 48 times. I have an x here in the numerator position. And this is all over. I can make the negative 2 a positive exponent by moving the x squared plus 12 term down into the denominator position. So there's my first derivative. But to find the inflection values negative 2 and 2, I'm going to need to take the second derivative. So my negative 48, we're just going to leave it alone, times. I have a quotient, So I need to use the quotient rule. So the quotient rule says take the derivative of the numerator, which is 1, and multiply it by the denominator, which is x squared plus 12 squared. And then minus, the quotient rule says take the derivative of the denominator, which is, bring the 2 down, 2 times x squared plus 12, and then use the chain rule, so times 2x. So take the derivative of the denominator right there and multiply it by the numerator, which is just an x, and then take all of that. Notice I'm keeping the negative 48 off. Take all of that and square it, so I get x squared plus 12 squared. Squared is going to be x squared plus 12 to the 4th power. And then I want to simplify things a little bit so that this is easier to work with. So I have a negative 48. And then when I look at the terms in the numerator, I have x squared plus 12 showing up in 2 places. So I'm going to factor that x squared plus 12 off using the distributive property. So times, if I factor x squared plus 12 off of the first term, I'm going to be left with an x squared plus 12. And then when I factor an x squared plus 12 from this term, I'm going to be left with minus 2. So I'm going to have a minus. Minus 2 times 2 is 4, and x times x is x squared. And this is all going to be over x squared plus 12 to the 4th. And then I want to notice that I have an x squared plus 12 over an x squared plus 12 to the 4th. So I can cancel 1x squared plus 12 out of the denominator. And that's going to leave me with negative 48 times, here I have a 12. I have x squared minus 4x squared is minus 3x squared. All over, I get x squared plus 12 in the denominator raised to the 3rd power. And so there's my second derivative. And then I use that second derivative to find my inflection points. And those are either going to be when the second derivative is undefined or equal to 0. But my second derivative can't be undefined because x squared plus 12 cannot equal 0 in the real numbers. And the only way to get a 0 in the denominator is to cube a 0. So I don't need to worry about that. So the only thing I have to worry about is when will the derivative equal 0, and that can only happen when the numerator is equal to 0. So if we have a rational function, it will only equal 0 if the numerator is equal to 0, and I have a product of 2 terms here. Negative 48 can never be 0. So the only way for the second derivative to be equal to 0 is for 12 minus 3x squared to equal 0. So we take 12 minus 3x squared, and we set that equal to 0. Adding the 3x squared to both sides, we get 12 equals 3x squared, and dividing by 3 on both sides, we get 4 is x squared. And then we take the square root of both sides, so we get plus or minus the square root of 4 is 2. So those are going to be the x values for our inflection points. It's going to happen when x is negative 2 and x is 2. If the problem is asking you for the location of the inflection points, so once we find where the second derivative is equal to 0 and we get those x values, if we're being asked for the location of the inflection points, then we would plug negative 2 and 2 into the original function f of x. So we would take and say, what is f of plus or minus 2? What is f of plus or minus 2? Which would equal 24 over plus or minus 2 squared. And the reason why it's easy to work with plus or minus at the same time here is this squaring is going to kill the negative sign. So I'm going to wind up getting the same result whether I plug in the plus or the minus 2. And so we would get 24 over plus or minus 2 squared is just 4 plus 12 is just 24 over 16. And it looks like 8 goes into both of those numbers. So 24 divided by 8 is 3, and 16 divided by 8 is 2. So negative 2 and 3 halves, and 2 and 3 halves would be the locations of the inflection points. So once we know the x values for the inflection points, we combine that information with the domain of the function to establish our test intervals for the second derivative. So the domain starts at negative infinity. So we're going to run from negative infinity to the first inflection point, and that's going to establish our first open test interval. So from negative infinity up to negative 2, that's going to be our first open interval. Then we're going to run from negative 2 to 2. We're going to run between the two inflection points. We're going to run from negative 2 and 2. That's our negative 2 to 2. That's our next test interval. And then we're going to go from 2 to infinity, because that's the part of our domain there. So we go from 2 to infinity for our last open interval or open test interval. So those are going to be the 3 test intervals over which the original function f of x is either going to be concave up, concave down, concave up. So that's establishing 3 test intervals. And then the test values are values we're going to plug into the second derivative to determine whether the second derivative is positive or negative. So our test values need to be in our open intervals. So for this one, x equal negative 3 would work. Between negative 2 and 2, we see that x equals 0 is in there and will be easy to work with. And between 2 and infinity, x equal 3 would be a good test value between those two numbers. And then it's just a matter of plugging our test values into our second derivative right here to determine whether the second derivative is positive or negative. So we take f double prime and evaluate it at negative 3. Which will equal, we get negative 48 times 12 minus 3 times x squared, so 3 times negative 3 squared divided by x squared, so negative 3 squared plus 12, that whole quantity cubed. And then we start to simplify. So we have a negative 48 times negative 3 squared is 9 times 3 is 27, and 12 times 27 is negative 15 over. We have negative 3 squared is 9 plus 12 is 21. We have 21 cubed. And I don't need to know the number that I'm going to get. I just need to know what the sign is. Is it positive or negative? So right now I have enough information to stop and determine whether the second derivative is positive or negative. I have a negative times a negative is a positive, divided by 21 cubed is a positive. So I have negative times negative divided by positive is positive. And if the second derivative is positive on an interval, I know that my graph is concave up on that interval. So I conclude that my graph is concave up on the interval from negative infinity to 2. Now I take x equals 0 on the open interval from negative 2 to 2, and I plug that into my second derivative. So f double prime of 0 equals, I get negative 48 times, and when I plug it in, I'm going to get 12 minus 3 times 0 squared is just 12, divided by 0 squared plus 12 is just 12 cubed. So 0 is easy to evaluate, and now I have enough information to determine the sign of the second derivative, because I have a negative times a positive divided by a positive. So negative times positive is negative. Negative divided by positive is negative, so the second derivative is negative. So I'm concluding that my graph on the interval from negative 2 to 2 is concave down because the second derivative is negative. And now I need to plug 3 into my second derivative. What I could notice is that because of the squaring in my second derivative, plugging in 3 and negative 3 will give me the same result. So I should get exactly what I have right here when I plug in a positive 3. So in other words, f double prime of positive 3 is going to equal still the negative 48 times 12 minus 3 times 3 squared over 3 squared plus 12 cubed is going to equal to negative 48, just like I had here. And then I'm going to get 3 times 3 squared is 27. 12 minus 27 is still going to be negative 15 like it was here. Divided by 3 squared is 9 plus 12 is 21 cubed, just like I had here. And so I'm going to come to the same conclusion. A negative times a negative is a positive. A positive divided by a positive number is positive. So the second derivative is positive, which means my graph is concave up from 2 to infinity. So I conclude that my graph is concave up. And now I need to summarize these results. I'm going to erase this calculation of the inflection point location so I can write a little bit more on this slide. So I'm going to draw a conclusion. My graph is concave down. When does that happen? Well, that happens between, using this box down here, between negative 2 and 2. So when x is an element of the interval from negative 2 to 2, my graph is concave down, and my graph is concave up when x is an element. The first open interval over which I was concave up was the interval from negative infinity to negative 2. So from negative infinity to negative 2, using this right here. Union, I need to add to that the other interval over which I was concave up, which was the interval from 2 to infinity. So union, the interval from 2 to infinity. So those are the open intervals over which my function is either concave up or concave down.